right, so I'm going to do something a little bit different this class than I've usually done, right? So I have on the schedule, which I'm sure you all pay close attention to, that next time is the review, for which the exam will be on, well, a week from today, right? So the exam is just going to be basically what was on the homework and what's in the labs. There's not going to be anything too new or surprising, right? And normally I do what some professors do, right? I do one review. What I'm going to actually try and do is I'm going to do both today and tomorrow as reviews, with the perspective of trying to tie all of what you know together, right? So I've made a bunch of changes to this class. I don't know if you went back and watched any of my old lectures that were recorded for previous courses, in that's been a big emphasis for me, right? Is to help you guys understand that everything is linked, right? We know the gates. When we build a big complicated circuit, or we're given a complicated circuit, we can use like Boolean Algebra to simplify it down. The reason we teach Boolean Algebra, right, is to understand the language of computers, essentially, right? And we can analyze using the typical analysis, right, where we write the equation of each gate until we get to the end of the final output. Or we can use like truth tables, or we can simplify using K-maps. And we have all of these tools, but they're all related. Everything is the same. So what I'm going to do today is I'm going to start just going through the homework that has already been due. So I'm going to do some assignment questions that are examples. I posted homework 1, so I'm not going to do very much in there, except for as an initial reminder, because it's been several weeks, right? And we like to flesh out all that information as quickly as we can. And then we'll move on from there. And next time I'll look back between now and Thursday and see what we haven't reviewed yet, and if I can't bring things in, because all I have scheduled for today anyways was talking about the design process. How do we design something? Well, it turns out the design process can be talked about 2 different ways, and the 2 different ways that you're going to think about them is an algorithmic design process, which we're going to get more into with the VHDL, so I don't need to talk too much about that. And the other one is, how do we build a circuit, right? How do we figure out what we're supposed to do? And the first step in that is always understand the problem, right? What are we trying to accomplish? So when we do that, we always going to start, well, for now, right, we're going to start with the truth table, because a truth table tells us what we're going to do, what we need to do. And we need to understand certain mechanical objects, certain functions, certain items in order to understand the digital logic that we're trying to design. We have to know it's possible, right? So let's talk about a new device. I haven't talked about this device very much, if at all, and it's a very helpful device. So let's say that I have one ADC. Probably should have a capital D. I don't know why I do that all the time. So an ADC is what's an analog to digital converter. Now we've talked about analog and digital signals, right? Analog being the real world and the digital being computers. More specifically, analog is anything that has an infinite number of values. Now, we can have an analog signal. We can have, say, an audio amplifier that is attached to your phone that goes from, say, 0 to 5 volts. That's not the real voltage, but let's pretend, right? So I go from 0 to 5 volts. In the analog world, there are an infinite number of values between 0 and 5 volts, right? Because I can have 0.35979 off into infinity, right? There is an infinite number of analog values between 0.3 and 0.4, right? It doesn't matter really how small I slice an analog value, as long as I have 2 analog values that are different, there's an infinite number of values between them. That's analog. Digital is defined by its number of bits, which we now know from our ability to count in binary, right? If we're counting in binary, we go 000, 001, 010, and so on. And each one of those columns has a weight. In decimal, we call them the ones place, the tens place, the hundreds place. In binary, we have the ones place, the twos place, the fours place, right? Decimal, base 10, meaning that we're going to go multiply by 10 every time we go. Decimal, base 2, we get twice as big every time we progress up a column, Okay, so what an analog to digital converter does is on one side, it takes some analog signal, which we very often represent by just drawing a sine wave. And on the output side, it's going to output, let's say this would be a 1, 2, 3, 4, 5, 6 bit digital value. So what that would say is within whatever the range of my ADC is, and just like any digital logic, because unsurprisingly, it's going to use AND gates and comparators and that kind of thing, right? We built a comparator already. That was one of the missile launch lab essentially was a comparator, as was the, well, we had the exact comparator lab, right? It was just asking is A greater than B. So we built a comparator. Comparator is nothing new. ADCs use comparators. You will learn about why if you take my sensors course when you're a senior. So the analog to digital converter is going to take a 6-bit binary number. Well, let's simplify down to 3 bits because I don't want to have to draw a whole bunch. So I'm going to have B0, B1, B2. I'll rewrite that so it's bigger. Okay, so I have analog to digital converter. You guys don't have to know what's inside of it to understand that this is a block diagram, right? This block diagram describes the function of a circuit. Well, let's suppose that we want to use this analog to digital converter for more than one circuit. Because it turns out the ADCs are very expensive compared to almost anything else we build. So I'm going to have something like circuit 1 and circuit 2. And then what I want is I want some kind of circuit that chooses which one of these does the ADC record. Okay. All right. This is a real application for this device that we're about to build. This would end up being what we would call a mux. There are 2 different types of mux. We're only going to worry about one. The one we're going to worry about isn't this one. This is an analog mux because it's muxing through analog, right? But I want to start with an obvious reason, right? Something that makes sense. To explain why we would use mux is we want to choose to either record from C1 or C2. An example of this is in your car. In your car, you have basically an upstream and a downstream emissions detector. They basically put 2 sensors in your exhaust pipe to measure what gases are going through it, as well like the oxygen concentration, the carbon dioxide concentration, and so on and so forth, so that it can feed back information to your engine to adjust how the fuel is being burned, basically, right? And so these sensors, they're like $40 or something per sensor. And then they go in, and in order to make the decision, they have to get converted to a digital value because it gets processed by your car's computer, right? Your car makes decision. In fact, your car has lots of little computers in it. In this case, it has like a special emissions computer. And if these values are reasonable for, say, oxygen, then the output tells the computer that, hey, these values are reasonable and everything's okay. If not, it throws an error and the car either puts a little warning light on your dashboard that you ignore for the next 3 months, or it adjusts something. If it can fix it, it will. So the mux that we're going to use has a symbol, actually, it turns out. Usually comes out of the middle like so. And then it just needs a select signal that just says which one. If you put a 0, let's take C1. If you put a 1, let's take C2. So now rather than designing an analog mux, which requires thinking about it in the time domain and infinite number of values, I can give you guys a whole new component, right? This is a new component. We haven't done anything with it. And yet we have all the tools we need to figure out how to build one of these. In digital anyways, right? Let's build a digital mux. This is the design process. I tell you, nothing more then this is the schematic. I want you to build a digital version of, and it can come out other side, doesn't really matter, this. We understand in the digital world, everything is made out of gates. There are these fundamental building blocks, just like your body is built out of elements, right? You have to go divide down to the smallest possible block. And really transistors are smaller, right? And we know somewhat about those and we could abstract them, but our real useful building tool is gates. And when we start, we just say, okay, let's build a mux. Now, there's two ways of doing this, and I didn't teach you one. One of them is the variable entered maps that if you didn't read the instructions on homework about 4, right, with the K-maps, that have weird letters inside of the K-map. Did anyone see those and panic? You guys are much better than my night class at reading instructions, apparently. No offense to the night class that ends up watching this recording. So anyways, what ends up happening, right, is we just use a truth table. We'll go the way that we do now, which is to say, here we go. I'm going to call this F. F is always a good one, right, for the output. We can do what we usually do, A, B. So now I know what my truth table looks like in general. We have to choose the order over here. It doesn't really matter as long as we're consistent. What I like to do is start by whichever signal makes sense as kind of a grouping variable is what I'll call it, something that everything else is a subset of, just meaning that if a select is 0 or select is 1, right, it's a digital signal, binary 1 or 0. I'm going to use that as my grouping variable to say that it changes the slowest, because I want to look at what happens in different conditions for select. So are we okay if I just write S? We understand S is select, and then I say S, A, B. I drew this block. That means those are my inputs. Now, this is something that I would hope that you guys would be able to do, and by now, and certainly by the end of this class, which is to see nothing but a block diagram, be given a brief description of what it's supposed to do, and then go build it. Let's do it together, right? This is the design process. Okay, I've identified my inputs. I've identified my output. Remember when I had you do this in the homework where I said, what are the inputs of this alarm system? What is the output of this alarm system? This is why. What are my inputs? What are my outputs? What are my possible variables? Well, A and B, I'm going to start 0, 1, 0, 1. And I'm going to stop here for just a minute because I'm only going to consider A and B for just a little while. And then go 0, 0, 1, 1. So A is an input here, B is an input there. And all I've said with the description is F wants to be able to choose based on the select signal, which one do I take? So let's start with the simplest version, which is to say select 0, right? We'll take the first group. And so I'll take the situation in which select is 0. Well, if select is 0, then F is A, right? So I go A, select is 0, F is A, 0, 0, 1, 1. Okay, well, let's expand my table. Now I have 8 rows, hopefully. If I have 8 rows, I have 8 different numbers from 0 to 7, right? Right now, this isn't considering numbers. It doesn't really care what the numbers are. And now I can go ahead and say, well, let's look at this and say, now if I select is 1, what is F? B, which then I just go look at B and I say 0, 1, 0, 1. There, I've described a digital mux. Now, what do we do next? We build it. How do we build it?
Make an expression that represents it.
Yeah, that's a perfectly fine expression, right? We could say that F is equal to the sum of the minterms, and we would just go look and say 0, 1, 2, 3, 5, 7. 2, 3, 5, 7. I could give you guys that, you know exactly what it is. We could write it out and we would know things like, well, these two are logically adjacent, so they're going to simplify, right? Because they only change by the b variable. And guess what? These two are logically adjacent, so they're going to simplify. So we already know that they're going to simplify. So we could write the expression and do that, right? And now we have Boolean algebra, which we've done. And so we say, okay, well, what are my minterms? I'm just going to say, it's S. I'm going to put S first, SAB, or SAB, or SAB, or SAB, right? Because all of my minterms have all of the possible variables to start, and now I just have to go figure out where the bars are, as pointed out here, and it's not S, not B, as you just said. Next one down, the bar is just on S. Over here, these two, middle one gets a bar, no bar on the last one. We've already identified that they're logically adjacent. We already know they're going to simplify. So there's no puzzle here, right? There's no like, oh, do we have to complexify? Do I have to add an extra term? Because I already know these two are going to simplify together. Well, it's the same thing as a K-map, right? This is how we know they're going to simplify when we're doing Boolean algebra, which is to say I have this not SA, the B changes. What happens to the B? It goes away, right? It's the thing that doesn't change because I'm going to factor it out and have this not B or B. What is not B or B? 1. So if I have an AND gate and I have S, A, B, like so, but instead of B, I erase it. I attach BCC to it. Now it's a 1. What is an equivalent expression for the output of this AND gate? S and A. Right? Because that B is just 1. Well, that's all I've done here. So I've created a 1, attached it to the 3 input AND gate, realized that the third input doesn't matter. Now I have a 2 input AND gate and it's a simpler circuit. Right? My algebra directly represents circuits. They're showing me ways to build an easier circuit. Okay, so now I have not SA and now that we've done it, we can do the simple version, which is to say the A is what changes. The A goes away, so I have SB. Great. Now I have not SA or SB. That feels pretty good, right? It feels likely that there's no way I'm going to simplify this further.
Yes.
There's not actually. I don't see any way.
Right.
Because like this not SS feels like maybe, but the fact that they're ANDed with 2 different terms that are unrelated, I don't see any way this is going to happen. But if we wanted to be sure that we simplified it, what would we do? K-map. We would just go write the K-map. Once again, we have to choose where this is in general on the exam. Fortunately for you, I'm going to try and remember to give you guys the variable orders, the mapping of this, because it makes my life easier to grade. It makes you guys happier because it's less confusion. But I might ask a question on one, right, that would be to set up a K-map. Right, that would be a reasonable thing to ask you to do, which is just fill in the K-map or go the other way. Given a K-map, draw me what is the truth table. And the only trick there, right, is to keep in mind what goes where. Well, if I'm going to go left to right, which is fine, I can go right to left. The way that I like to do it is I like to go S and then look at, well, if S is changing slowly as I progress through, that's all I'm looking at. What changes the quickest? Well, if I look at what these K-maps do, is this variable, the rightmost variable that changes the most often, basically as I progress across the right. So the most often is B, A. That's how I decide, is because I like to keep the things that move fast as I move across the column, because what that says is, well, the first 0, 0, 0 is always 0, right? The first is always easy to find. Doesn't matter the order, it's always the top left. And then you might have minterm 1 here or minterm 1 here. As long as you build this intelligently, you could do weird things that it is actually over here. That is a possible choice. I like to avoid that one. If it starts to happen, I'll just redraw my map and make it what I like it to see. Because now all I have to do is find where is the next one, which is S is 0, A is 0, B is 1. S is 0 here, A is 0 here, B is 1, and my output is 0. Now I know the direction that this K-map goes, and as long as I remember to flip the order, it's easy, right? I'm just going to go down 0, 0, 1, 1, 0, 0, 1, 1. Next group 0, 1, 0, 1, 0, 1, 0, 1. Flipping that order is important. We can go grab a different color, group those two and those two. I now have ones. I have, well, S doesn't change on either of these rows. So whatever F is going to have an S in it, S something or S something. In this case, S is 1. In that case, S is 0. And now I say, okay, well, what doesn't change? A changes here, B doesn't. So the B sticks. When I have S is 0, did I do something weird here? This is going to be really funny if I get it wrong. So S is 1, A changes, B, SB, S is 0, A doesn't change, A. There we go. I just flipped the order of those. They're linear, doesn't matter, right? The order of the addition doesn't matter. Order of addition doesn't matter. Same equation. Now I look at this K-map. What does this tell me? What's the problem with the circuit? Implicant. Hazard. A hazard. Yes. There's a static 1 hazard because I have adjacent ones that do not share an implicant. So the implicants, don't forget this, implicants are the circles. Completing coverage means I'm done. Coverage just being that I have all the one circle. This is a minimum implementation. However, it is not hazard-free. So what we do, if we want to fix the hazard, what do we do if we fix the hazard? I add an implicant, which is just to say, let's make them share. Now I'm going to add an extra path if I don't want there to be a hazard. Now, orange is optional depending on the objective of your circuit. In general, the concept is if you're going really fast, hazard matters a lot. If you're not going fast, you can usually design smart logic that doesn't care about it. Basically, that's where it comes down to. In this case, a lot of the times with the mux, we don't really care because it turns out it's being controlled by the select signal and whatever brain that we end up building for our circuit, which we're going to build eventually in this class. We will learn to build what is called a controller that makes decisions based on the input conditions. And it can do things like take into account timing. So as long as it has a control signal to it, maybe we can handle it there. If not, if we're not confident, we'll just make it a little bit more complicated, which is add another AND gate and another input to our OR gate. How many more OR gates does that mean if we're limited to 2 input OR gates? 2 more, right? Because in order to build a 3 input OR gate out of 2 input OR gates, I would do this. But can we do better? Right, this is 2 inputs. This is now 3 inputs where this is always 0. So if I call this A, B, C, well, this output is A or B, and this is C or 0. So we just make it C, right? Because what is C or 0? C, right? The 0 can never be true. So this circuit is functionally equivalent to that circuit.
And there's no hazard.
Yeah, there is no hazard because there is no input signal that has more than one delay path. We're safe. So anyway, this is a nice way that we can check like 3 input OR gates to make sure that when we made a decision, was it smart, right? Did we make the right decision? It doesn't matter if we get it wrong the first time, as long as we can recognize that we have all the tools we need to simplify. That's why we analyze, did it build right? Right, so I have dot SA or SB, I can go build that circuit. I have 2 ands with an OR. S is here. There's my not SA or SB. And now we can see the hazard, right? Because S has 2 different delay paths, and there's not an extra path there to address the issue. And we kind of know that. It turns out if we look at the K-map, the S is going to be the issue because S is the one that changes over the adjacency. We don't have to know that, but that's a trick that you can use to verify your sanity if you're curious, right? Is it is predictive of not only is there a hazard, but which signal will be the hazard. We have a circuit. All right, now we want to build this down in the lab. Let's say I want to build a mux. What's the next step?
Put together or make it hazard free.
Do we have the parts for this? Change it to NAND, right? We need to do it. The way that we do this is we add inversion bubbles, right? A bubble means not. And we're going to start left to right because that's the way that I've taught you. And basically every circuit that I give you will be solvable through this. Not, right? This is just keeping in mind this type of circuit architecture with the inverters, where if this signal is X, that makes this not X, this makes this not X, which is still X, right? That's all this double bubble is doing, but this gate is nonsense. So there's kind of this intermediate stage where I have the 2 ands, goes through an inverter, into my inverted OR. Well, this isn't really right. I fixed one, but now I can keep pushing these bubbles all the way there. And then I have bubble, bubble. And then we just use the fact that this is equal to that. There's a theorem that tells us this in math. What is the math theorem? The expression for this, right? Let's X, Y, Z. We would say Z is equal to not X or not Y.
Oh, I don't remember the name of the theorem, but I know what it is.
De Morgan's, right? Then we do a De Morgan's operation over this, and we're now calculating essentially not Z, right? In order to keep the signals the same, I need to say not Z, which then, because if I not one side, I have to not the other to make them stay equivalent more or less. But now we would say, well, flip the sign, so it's now not X and not Y, which is XY. But remember, this is not Z now because I inverted that sign. So this is not Z equals that is equal to that. So therefore Z is equal to not XY. Guess what? That's an AND gate. Did everyone follow that process? Right. All I did with the knots here is just to keep track of the fact that if I, like in algebra, if I have I don't know, 5x is equal to 4y, and I'm trying to solve in terms of x or something, I can divide both sides by 4, right? Well, same thing here. If I invert one side, I have to invert the other side. It's just keeping them equivalent and then recognizing that that inverter is doing the inversion for me. So now I have kind of this not situation again, and I get an AND gate. That's why they're equivalent, is because the math tells me. I went the other way, right? And I told you that they're equivalent, and then I taught you the math, which is fine, but I want you to make sure that we understand that in this design process, it's the same thing. The math is the circuit. All right, so take those, push them there. I have nothing but NAND gates. I can go throw this onto a circuit. Everything is fine. Now I did this to you, this type of design. Oh, before I move on to that, right? And this is a mux. So what it's going to do is it's going to choose what input. Well, now let's say that I want to use this mux that I just designed and I have a 2-input mux. Now I want a 4-input mux. Because let's say I have a fancy new car that uses 4 sensors, and the output of these sensors is 0 or 1, right? Basically, my sensors are telling some circuit, it's telling my computer, am I okay or am I not? Right? 0 or 1. Technically, that is an analog to digital converter, right? If I have a sensor that is a comparator that says, is my oxygen level above or below some threshold, then the output is on or off, right? Make sense? You can actually use your inverters as a comparator for this, right? It turns out, because your inverters here, if I input a slow ramp like this, at some point, it's going to toggle over and say it used to be a 0, now it's a 1. So what the output's going to do is it's going to invert this. So it's going to start as 1, and at some point it's going to cross that and it's going to drop to 0. So what do we say? Analog, digital. The input can be any value between 0 and 1, or 0 volts and 5 volts, right? But the output is always 1 or 0. So let's say this is all our sensor is doing. Let's say our sensor is just looking for some percent oxygen. Okay, well, let's say there are now 4 sensors because it's a fancy car and they like to charge you extra money for all these sensors as they go bad because they make a ton of money off of maintenance. And so now there are 4 sensors that are monitoring all of this, and we want to use our muxes because the computer is expensive. We don't want one computer for everyone or one input, right? So like if you go look at a little microprocessor, it has a limited number of pins. And so instead of using 4 pins, because pins cost money, right? That's kind of why your packages are the standard size, is because we could put NAND gates in a bigger, longer package that has like 24 of them, but that package is expensive. Pins are expensive. I don't want to use 4 pins on my microprocessor. I want to use 1 pin to evaluate if any of my 4 sensors are working. What do I do? 4-input mux, right? I mean, the OR gate could work, but let's use the mux for now. Yeah, that's actually not a bad idea, right? The 4-input OR gate would just be fine. Let's say we're going to build with muxes. But not a bad idea. How do we build the 4-input mux? We just did it. How do we build a 4-input mux? Or we did the 4-input OR gate. How do you think we do a 4-input mux? Yeah, the same way. Let me use the black and differentiate. So I have 1 component. I now take another component. Right, and this is the equivalent of me reaching into the bin and plucking out another mux. They're both called 2-input mux, right? But they're different mux. So it's helpful to give them different names. We're going to call him M0 and him M1. Make sense? I need another one because I need to combine those signals. And actually, this is not how I'm going to name this because I'm going to put them as I should. So they have ports A, B, F, and S. And its name is M0. Similarly, his name is M1 with ports A, B, S, and F. And the same thing is true here, A, B, S, F. There we go. Why did I move my signal names A and B from outside the box to the inside the box?
Signifying that they're like converters from the inside. We're going to use different variables on the outside.
Yes, yeah, I'm using different variables on the outside, which is another way of saying that on the outside, I want to have signal names, and on the inside, I have port names, right? This is one of the most confusing parts of that last lab that we just did, or yeah, you guys just did it, right? You built the full ladders together, right? That is one of the most confusing parts, which is the differentiation between ports and signals. But this is an important idea. So all of my parts, M0, M1, and M2, all have the same name of port because it's the same part. It's just a different instance. That's the word, right? It's a different instance of that same component. Okay, so a different instance of the same component. Now, this is just vocabulary. I know we're not in English class, but if you don't know what the words I'm saying mean, specific to engineers, right? Because instance component mean different things depending on who you are. Turns out computer science, they use instance all the time. It means something very similar. Does anyone know what instance refers to in computer science? It's fine. Let's say I open up my Windows computer and I launch the calculator app, right? And I launch another calculator app. I can run two calculator apps side by side. Each one of those is an instance of that application. It's the same application. I'm just running it multiple times because I want to do different things with it, right? It's the same idea, right? It's very similar because computer science and engineering are very close together, right? We're in the same college for a reason. So instance, that's all this means, right? One of a thing. Okay, now I have this. Now all I have to do to decide is my select signals. What do I do with my select signals? So I'm gonna have ports A, B, A, B, A, B. So let's differentiate, but I don't have to, right? I could have an input bit that is my sensor. Well, this is a port S, but we can be confusing if we're not careful with our names, because eventually when you're writing VHDL, you guys are gonna name your ports, you guys are gonna name your signals. And you're going to be very clumsy with your port names and your port signals in the beginning until you learn to hate yourself for being very clumsy with the variable names, because things like this will happen where you're going to call, well, this is sensor 0, and this is sensor 1, this is sensor 2, this is sensor 3. Right? This is allowed because this S and that S are not the same because this is a port S. Inside the circuit, it knows that the signal name is S, but the outside world views it as a port, okay? This is all the block diagrams are telling us, so that when I draw these pictures, I give it a port name, we need a signal name. Because this output port that's called F, doesn't make a signal called F. It makes a signal called Jeff, right? It doesn't matter what I call it. Down here, we could be Josie. Those are fine signal names. I mean, not really, right? Because they don't tell me what they're doing. But I'm allowed, I could do that. It's just pulling a wire out, it's pulling out one of your wires out and saying this one is named Josie, and then you plug it in. You know that that orange wire and the orange wire you named Jeff are different orange wires, and you've named them differently to keep track. That's all. That's all we're doing with this. Is this an orange wire? That's an orange wire. We gave them different names to keep track. We don't need those names because we just look and see where they are, but a computer needs a name. So that's why I want this, is to make sure we maintain a logical connection in our minds between the things that we draw, the things that we build on the breadboard, and the things that we type into the computer starting next week. Okay, that's why I'm emphasizing these, is because it is all related. This is all one big story that is designed to make you guys go get jobs starting at 75,000 plus a year, right? That's why you're here, I assume, is most of you have some combination of you want to build things, you want to help people, and you want to make a lot of money doing it, right? This is why, this is what we're doing. Okay, so now I have this, I have my weird signal names. Now I'm left with the select signals that I need to figure out how they work. Guess what? It turns out we can start guessing what they should do. But at very minimum, at most, I need 3 different select signals, right? So we could say that, well, let's just draw a truth table and see if, does a truth table help us think through the function of this particular circuit? Well, if I have, and I'm going to just start calling these ones, I need to give them a name so that I can start talking about what they do. Otherwise, it's going to be really hard. Well, what if I realize I gave bad names and now I call this one M0, this one M1, this one M2? Well, now I've done kind of a bad thing, because now it's really confusing, because now I have a signal name, which is the same of my component name. And I'm going to go, ooh, that wasn't very smart, right? And I could go back and rename all of my variables because I just realized I did something dumb. Or I could just bite the bullet and be like, all right, well, I have to figure something else out because M's are already taken. And so I'm going to go, P is fine, P0, P1, P2. I don't like P because it is not descriptive, just like Jeff and Josie. Right? They're not descriptive. We like descriptive variables. I failed that, but it's okay. And now I go ahead and I say, well, what happens if P0, I'm going to count down, P2, P1, P0, S0, S3, S2, S1, S0, and I can start drawing my truth table, and this becomes an absolute nightmare. Yes.
So in VHDL, are you able to put in comments to be like, this is what this variable is actually?
Absolutely can. Okay. We could do this. We could start writing the truth table. We don't have the K-map tools to solve this, but we could write the minterms and start puzzling through, right? This is within our abilities. It stretches them, and this would be 2 to the 4 plus 3 long, so 2 to the 7 rows, which is kind of obnoxious. Or we could say and recognize, well, it turns out that if P2 is 0, does it care what P1 is? Not at all. And if P1 is 1, does it care what P0 is? Not at all. So that would be really nice, because we could then fill in this truth table with a million don't cares. Or we could just implement it as literally doesn't care. What is happening to the other one? Now P0 feeds both of them, and I just treat the first one like, well, if this is 0 and this is 0, I take S0. If this is 0 and this is 1, I take S1. If this is 1 and this is 0, it takes S2, 1, 1, is S3. So now I have a 2-bit control signal called P. Now, this is kind of cool because now if I draw this as a block diagram instead of worrying about this big complicated truth table, because this is where we're going, right? I need you to understand that these truth tables help you think about the problem. They help you solve the problem. And in fact, the computer uses these truth tables to help simplify the problem for you. We just have to be aware that things like hazards can show up and delay paths matter, right? That's where this connection is going. But now I've got this. This is part of that design process, right? We're just going to use something we're familiar with, the OR gate stacking, and apply it to something new. We've done it with ORs, we can do it with ANDs, we could probably figure out with NANDs maybe, right? New design, I built the thing, now I come over. Since this port is F, I could still call that port F. I'm going to call it something else. And I'm just going to call it M. I think M's okay here. Inside, it might be confusing the M0, M1, and M2, but once I have abstracted it to a higher level of a design, now I have a 4-input mux. And you and I both know that this and that are the same circuit. And to the outside world, S0 is a port, and inside of it, it's a signal. And outside of the world, A is a port, but inside of this, it is a signal. This is what we call hierarchical design. This is a hierarchy, right? Which is this goes above this, goes above this, right? It's a pyramid, basically, that scales down. There is a level of connection in here that we've abstracted to here. And now if I draw one of these, you guys know what I mean. You know that this represents a really complicated circuit that you can draw all the way down to the transistor level, right? Please don't be a test question. That won't be that complicated because that would take a long time. This is a lot of transistors, right? However, it's not that many once you recognize that we've converted it to an AND gate, and we can draw the NAND gate as transistors, right? Just using the pull up and pull down networks. And then it's nothing but NAND gates. So now it is 1, 2, 3 times 1, 2, 3 NAND gates that are all 4 transistors. So it's 4 times 3 times 3 transistors, and we're done. Not counting the inverter here. So I need 2 more for each one of those, right? Inverter takes 2. We can count. So I could ask a question. A more reasonable question is to draw this and ask the question, how many transistors is it? What is the minimum number of transistors it takes to build that? And you know, maybe not off the top of your head, but you have all of the tools that you need to figure that out. Right? NAND gates, lots of confusion, puzzle looks there. So let's draw it. So we know one of 2 things is going to happen. We need a serial pull up and parallel pull down, essentially, is basically how we're going to build everything. And if we don't know anything besides that, then we're okay, because we're just going to start drawing and be like, okay, well, there's my serial pull up, and here's my parallel pull down. And now we ask ourselves, is this right? Did I build a NAND gate or did I build a NOR gate? It doesn't matter if we know, because we know that PMOS devices close or turn on, right? Closed is on. Close the switch, allows current to flow. Closed is on. They close when they see a 0, because they're practically the same conceptually as an NMOS with an inverter, right? That's all the bubble is saying, is there's an inverter here into something that is functionally an NMOS. And now if I put a 1 here, a 0 is here, and now it's off, which is to say a 0 is on. Yeah.
And you know it's a PMOS just because they're in a series.
No, no, it's not because they're in series. It's because, so there's 2 clues that something is PMOS. The first clue is the bubble. And the second clue is that the PMOS will be always in your pull up network and NMOS will always be in your pull down network. And you'll learn about why in later classes at ECE 3110 that talks a little bit about device physics. And there's a whole class that Dr. Jackson teaches that is all about device physics. That will explain really in depth how these things work. But as it stands, we just have to know PMOS go on top, otherwise they won't work at all. NMOS go on bottom, otherwise they won't work at all. As I've said before, I don't really have a useful mnemonic to memorize that, because unfortunately, it's not alphabetical order top to bottom. It's not positive because P is actually inverting and N is negative, which is right. Any mnemonic that I have can get confusing, because I can be like, well, the N is negative, so therefore it attaches to the ground. But you might confuse that with N is negative, so it has the inverter. So anyways, it's just memorization. Unfortunately, I don't have a good mnemonic for you, but PMOS pulls up, NMOS pulls down. Otherwise, they don't turn on. That's all. As I've said, this exam, open notes, open book. They have books in the library now. They should have enough for everyone. In fact, I've actually managed to buy them more than enough for everyone for the first time in my life. And so if you have the book, you get to bring it in. You get to use it for the exam. You get to draw one of these pictures. In fact, you can draw an NMOS, a PMOS, and whatever else you want, right? NAND gate, NOR gate, whatever you want. I don't really care. However, when you study for the exam, make sure that you understand your notes and the book, because otherwise you will just run out of time. Because almost inevitably what happens is somebody shows up to my exam with nothing but one sheet of paper, sits down, and they've organized everything, and they pound through the exam in like 25 minutes. And then there's somebody else, or like 6 somebody else's, that are sitting usually in the back, no offense to you guys, with a giant pile of notes, staring at the exam for an hour and 15 minutes, going like, I know it's in here somewhere. So my recommendation to you guys, this is a good college study, especially if this is like your first or second semester, is create a note sheet, whether or not you're allowed to use it. In my case, you are, but creating a 1-page note sheet makes you have to think about what is the most important material on this exam. Fortunately for my class, you're allowed more than that, but having kind of the list of what is most important in one nice convenient spot will have made you write it down. You're familiar with where all of it is, and you're prepared. If you run into something weird, then you can go burying through your notes and hoping to find gold, right? That's what you're looking for. But that's my recommendation for studying. So now, back to this. You ask the question, is this a NAND or NOR? Well, just like with everything else, we use the same tools we've always used, which is a truth table. Truth tables are really great. Eventually, when you've gone insane, you get your PhD and you teach this class, you'll just be able to look at this and fill in the truth table with your mind. Until then, if you're worried about it, you draw the truth table and we say, well, A and B means there's 2 to the 2 possible rows, right? There's only 2 inputs, so there's only 4 rows. We use the little trick, or we remember how to count in binary. We say this, and then we say, well, if they're both 0, that turns on which ones, and we can go draw and say, well, the top one is closed because a 0 closes a PMOS. And the B is closed because a 0 closes the PMOS. In the pull down network, it's NMOS, it sees a 0. They're open. This is my circuit. What is the value of F? 1. Does my circuit light on fire? Probably not, as long as I don't mess up VCC, right? Because there's no direct path between VCC and ground. If there was, if I messed up somehow and this closed and that closed, then it's infinite current, right? Because of Ohm's law, V equals IR, which we would then move current I, which I know it's an annoying one, but I comes over here and we say V by R. In that case, resistance from positive to ground, there's no resistor, there's no resistance. Therefore, zero resistance, infinite current. Infinite current means infinite power, which means you've just started a fire, right? But that doesn't happen here, which is really convenient, which is why we do this kind of mixed pull up, pull down, pull up serial, pull down parallel, or vice versa. And we say 1. Now, what we've done this, what we can say is, well, now we can see that if either one of these is not 0, it's going to break and it can't be 1. So what you could do if you're paranoid, if you're not good at this, is go, well, let's address the pull up network. And then we'll address the pull down network, and then we'll address F. Okay, so you've seen me do this kind of multi-column truth table. This is just a little bit different way of using it, which is to say, well, now I know that the 0, 1 is not pulled up, because if either one of them is 0, or if either one of them is 1, it can't pull up. Well, we've seen a letter for this already, right? I've introduced Z, which is to say high impedance. It is just not connected. Z. Now the pull down. Now the pull down says if either A is 1 or B is 1, it's connected to 0. So now we say, well, in the pull down network, this 0, 0, it's not pulling down, so it's Z. But this one is, and that one is, and that one is. And now when I look at this truth table, what this tells me is that when this is driving a 1, this one is doing nothing. And when this is driving a 1, this is doing nothing. Driving 1, doing nothing, driving 1, doing nothing. As long as I don't have a situation where any given row has a 1 and 0. That happens, I have a problem, right? If a row has a 1 and a 0 in this type of drawing, I have a problem, because it is trying to both be 1 and be 0, and that starts a fire or melts your breadboard or whatever annoying thing happens. So since this doesn't happen, well, oh, sorry, these are 0s, not 1s. That's what I was saying on as 1, but instead it's 0s, right? As saying the pull down is driving, I should say 0. And so now, since the Z's don't matter, now it's 1, 0, 0, 0. What kind of gate is this? NOR gate, right? And if you're not sure, if you run into that problem, see F, let's just write F bar. This is kind of just a continuation from here because I ran out of room. What is F bar? 0, 1, 1, 1. What is that gate? Or. It turns out it is easier to recognize or and ands than it is nands and nors for us. And that's really just the way that we teach the class, and because we like to think of ones as ons, right? That's all this is saying is that's nor. I tried to build an and. I failed at this. That's okay. I just flip the pull up and pull down. It's now parallel. PMOS is on top. Serial NMOS is on the pull down. I will get a NAND gate. Right? This is how we can check and see if we've done something right. A good exam question for this kind of thing could be given a circuit, fill out a truth table, see if you can identify what it does. Right? That kind of type question. That's all you would do. Okay. Okay. Another good thing, right? Analysis type questions asking you what function does this circuit represent? And one of the ones that I like to do, because this came up, for anyone that designed the half adder, and actually I learned a lot from giving you guys the option. And actually when I went ahead and had the next class design the lab, because I have two classes and the other one does the lab after you, I actually just forced them to do a half adder as their first input. I'm actually going to draw this bigger. In the back, if I ever draw something too small, let me know, because I'm a nerd and I sat in like the second row through my entirety of existence, so I don't really know what it's like to sit in the back row, except for in semiconductor physics classes, in which case I sat in the back because that was an awful class. No ding on Dr. Jackson. I'm sure he does it better than the professor that I had, actually. Dr. Jackson is much better than who I had to teach that class. So, right, your professor is all the difference. If some of you find my random meanderings obnoxious, you probably hate me, and that's okay. I've already gotten the feedback that I'm the worst professor ever. In the same semester, I got the feedback that I'm the best professor ever, and it's okay, right? My personality is going to taint your view of digital electronics for the rest of forever. So I don't really like that the lab did this. They did it to simplify your guys' thinking about what it is. But really what we have is we have the output sum and an output carry out. And it's going to be the same for the full adder with sum and carry out. Right. And then they have the ports A and B. And we'll notice that the half adder and the full adder are different components. So the full adder, you are given a truth table to go design a circuit, and you didn't have to put a lot of brain power in how to build the circuit, just a lot of effort into making sure you didn't get your wires overly crossed and didn't fry your circuits and made sure that your powers were connected to the right spot, right? Whereas the half adder requires a little bit of thought, because the question is, well, a half adder is really a full adder that just doesn't have the carry in. That's all a half adder is. So this is where the confusion came, and this was my mistake when I introduced the lab, which is some of you are building a half adder and a full adder like so, and some of you are building a full adder and half of a full adder, right? Which is different than a half adder. So let's focus now, and let's get everybody on the same page. A half adder is a circuit that is a full adder that has no carry in input. So now, truth table, right? This lecture, if you look at the calendar again, it's about the design process. The design process here is I've now given you this circuit, build it for me. Turns out you can build each block independently, test them independently, and then connect them together. So suppose that you built your full adder and it worked and all the lights turned on correctly. Okay, now let's build our half adder, which is not yet going to be connected, right? This one is still having 3 switches connected to its inputs to choose A, B, and C. Well, this half adder, then I draw a truth table to go figure out, right? There's that clue in the lab, which is started with a truth table. We always start with the truth table for now. It's inputs A, B. Guess what? The C in doesn't really matter. It's not there. A, B, and this is the sum and carry out, because I need one column for every output. You'll notice that when we build a circuit, I don't really have a way of driving multiple outputs, because if it's multiple outputs, it will always have the same value, right? If I branch off this and come down here and call this alpha or something, alpha and SA are the same thing. So there's no point to having it. So it's one column, one output. All right, well, what is sum? Sum is as simple as saying, let's add them together across the row, right? Because that's what the circuit does, is it takes 2 one-bit numbers and adds them together. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2, which is 0 with a carry. Well, this gate, a lot of people would have pointed out that's an XOR, but we don't have XOR, so we had to build it as is. it doesn't, it's simple, right? This one is really simple because it is true if and only if A and B are true. There's my carryout circuit. I could do that in a K-map, or I could just skip to the end. But there's an issue, right? We don't have AND gates sitting on your desk. We have NAND gates. And normally what I've taught you to do is, well, I can put the bubbles here and then push 2 of them. But if I put the bubbles on an AND gate at the output, what happens? It's a NOR. I don't have NOR gates. So let's just convert this to a NAND. That's a 0. Right, the bubble, which makes this technically not CO.
So if you invert A and B with that.
I could invert A and B, or
Just the carryout.
here we go. Yeah, and 2 less transistors. Right, so ta-da, we did it. That's all, right? So sometimes we have to break from the rule. You're not going to have to break from the rule any more than this kind of thing with a half adder. But there is something that is really cool about this circuit that I pointed out in my other lab. So I have C. Let's do it this way. A, B, C, I, S, C. And I'm going to flip CO and S so that the numbers look right this time. Oh, no, I'm going to stick to the same because otherwise we're going to get confused. S, C, O. This truth table is the same thing, right? And this is the same kind of thing where if I asked you to build a prime number detector, you would just look at the binary numbers that are here and write 1 wherever there's a binary number. Well, in this case, I'm not detecting binary numbers. I am adding the numbers across the rows because there are now 3 1-bit inputs, A, B, C. Slide this a little bit so I can stand out of the way. 0 plus 0 plus 0, 0, 1, 1. And anywhere there's just 1, I can just go put a 1 in this column, right? Those are all 1s. That's a 0. 1 plus 1 is 2. 1 plus 1 is still 2. I know there's a 0 there. We know there's zeros here. 1 plus 1 is still 2. 1 plus 1 plus 1 is 3. 1, 1. Right? Now this was given to you. This was nothing new, surprising, unusual. But what's cool about this is, well, there's another way to think about a full adder, which is to say, I could, like you guys did, build this as a full adder, but just connect the carry into ground. Right? It's saying that in my addition, the first column can't ever have a 1 in it because it's not carrying from anything. So let's connect it to ground and move on. Well, if we look at carrying as ground, right? That's what this is. Well, what is S? 0, 1, 1, 0. S is 0, 1, 1, 0. Carry out is 0, 0, 0, 1. 0, 0, 0, 1. It's the same circuit, assuming that the carry out is ground. It just allows us to simplify the circuit if it's never going to be there. In some cases, like when you're building on your breadboard, it is much easier to build a half adder and a full adder. It turns out when we move on to code, when we start learning VHDL and describing it, turns out it's going to be actually easier to use a full adder there. Because if I were to build this, I would have to write one component. I'd have to describe to the computer one component for the half adder and another component for the full adder. Well, it's easier in VHDL to just use one full adder and assign one port to 0 and then just repeat it. In fact, this is what not next week, but the week after, I think is what's scheduled for. I'll have to double check it, maybe next week's lab, is we're going to build a 4-bit adder that will take 4 full adders. But we're not going to do it on a breadboard because that would be a nightmare, right? I mean, I could do it. I could have like each of you go to a group and each of you builds a complete full adder, and then you partner up with another group and you string those 4 full adders together and you would have a 4-bit adder. That would be possible. However, it is much easier to tell the computer, hey, I'd like a full adder. I'd like another full adder. I'd like another full adder. I'd like another full, right? And just do that again until you have as many bits as you need. In fact, we'll get even better at it than that. But this is our relationship. This is our design process, is build something, right? And then see if you're right or if you can do better. That's a totally fine way to be an engineer, is make something work and then make it work better. That's all I've got time for in class. We will have a more typical review next time. Today, I wanted to use the topic of design process to help connect everything we've learned together, because that's the most important concept up in this portion of the class. Thank you, guys.
Thank you.